are going in a clockwise direction. You could also reverse it, but it really doesn't matter. But just for convention's sake, this is what I've seen, and this is how I encourage you to do it as well. So now we can start talking about inserting to the back. And when we start to insert more, we start to notice a different trend emerge. So now let's say we have the following DList, and its next are all going in a counterclockwise fashion. Its prevs pointers are going in a clockwise fashion. Now we want to insert to the back of the DList, to the back of the sentinel. So what we need to do is we need to change the pointers around such that it makes sense, such that it still follows the same pattern. So what we end up needing to do is we say that the sentinel's next pointer will be pointing at this, correct? And the next pointer of this node will be pointing at this, and we want the previous pointer of this to be pointing here, and we want this previous pointer to be pointing back at the sentinel. And all that's happening is really all we're doing is messing around with the pointers. And I would recommend doing a lot of these, implementing a lot of these DLists, such as insert end, remove end, insert front, remove back, things like that, just to get a hang of what's going on, especially with pointers analysis. Really understanding what's going on with pointers, I believe, is incredibly important when studying data structures, as we'll be using DLists and a combination of SLists to represent more complicated data structures as we move on in this course. So you start to notice the following trend. When you want to insert or remove operations, any insert or remove operations ends up taking constant time in all cases, because all you're doing is you're rearranging pointers, and you're not walking through the DList or anything like that. Find, however, still takes big O of n time, because you have to iterate. Worst case scenario, you have to iterate through the list, but in the best case, it takes constant time if the first node after the sentinel or head.next is equal to the item that you're looking for. So we can now talk about the idea behind using a sentinel or a circularly linked list, and that is removing a lot of these small base cases that we had to deal with before. When you're trying to implement a regular DList, you have to use a lot of if clauses, such as inserting into a DList with 0 nodes, inserting to a DList with 1 node, so on and so forth. With a circularly linked list, there's only one base case, which is just constructing the sentinel, and then you're just adding to the front or the back of the sentinel, and that's all that's happening, and it's the same every single time. So I hope that helped your understanding of linked lists, and I hope that the thing to take away with this whole lesson is that what I'm telling you is just a basic understanding of what these data structures are. You can literally take a combination of these lists, you can add more pointers, add more references to augment the structure to do whatever you'd like, or to reduce runtimes of certain operations that you feel you'll be using more, depending on the data you're using. And that's really the beauty of talking about data structures, because you can, if you understand them, then you can morph them around and change references, add pointers, or change fields such that anything is possible. If you know exactly what data you're using and know exactly what operations you'll be performing on that data for any of your client-side applications in the future. So thank you very much, and I'll see you next time.